Progress.
Is there any questions on anything? Okay. Let's see. The second section of chapter 2. A lot of it is definitions. And the link is on As You Learn. Doesn't want to let me. So, oops, I went into the wrong. So when you're in your class, if you go to outlines, all those definitions are here. I am going to add to this because I didn't put any problems yet up. So this will get added too, but all the definitions are there. Under attendance and homework, if you haven't seen it yet, there's a project. Make sure you go on and pick which one you'd like to do. The link's in there. So you click this link and decide which man-made disaster you would like to do. An example is here, and then this is the link where you post. I get a lot of questions about where the videos are from class. They are right here. The thing you have to be careful of, like if I go into the regular dashboard, it's called My Media. Those are the ones I put up there. So if you're clicking on My Media, that would be if you put any up. But when you go into the course, it'll say Media Gallery. Those are the ones that I put for your class. So if you need to see what we did on one day, you didn't miss part of the notes, or if you missed class, you can go back and see all the recordings. Sometimes if there's something that's a little more difficult and students aren't getting, I'll make another video and put it in there, but I'll let you know. Any questions? I think that's everything. So section 2.2 talks about energy, work, energy, and power. Energy is the ability or capacity to do work. Mechanical work is done when something like the handle of a rowing machine is moved against a resistance force. The amount of work is the product of the force and the distance moved. So how much she is moving, and then the heat would be her energy. With each stroke, the handle rowing machine is moved about 3 feet against a resistance, and maybe 50 pounds of force. Now, if you want to find out the amount of work done, then those get multiplied. So how far you're moving, that's your resistance, and the force. 3 times 5, it's 150 foot-pounds. And there's a table we'll look at, but foot-pounds is a unit of energy. It's not the most common one, but it is a measurement of energy. Formula-wise, if you needed to use formulas, those would be given. I don't expect you to memorize those, but it's good to know how to use them. And I haven't ran into any in this section yet. You can think of energy as a kind of money that allows you to buy. That would be your action or work. To achieve the desired result, move a car, boil water, light the room, we have to pay for it with energy. After we've done that, energy still exists, but we don't own it, somebody else does. So when you have that energy and you use it for work or burning it off, then it goes elsewhere. It does not just disappear, though. After we've done that energy, it still exists, but is no longer in our wallet. You want to think of that idea as we're doing a lot of these problems, that we've used that energy to do work, and now someone else has that energy. It's not gone. Suppose that athlete makes 30 strokes per minute. Each stroke transfers about 150 foot-pounds of energy, so that her workout is transferring energy at a rate of 30 times 150, because she's doing 30 strokes per minute, 4,500 foot-pounds in a minute. Now, when you combine those, you're talking about power. Power is the rate of flow of energy. Because we made it a rate, 4,500 foot-pounds per minute, it's power. Now, don't get overwhelmed by all of these units and definitions. It's just good to understand them when we're using them, but I don't expect you to memorize them. Chemical energy. This is the energy stored in the bonds of a chemical compound and fuels that we burn, like gasoline, the fuel for an automobile. You could even think of the food you put in. It's a chemical into your body to give you energy. Burning, oxidation of these fuels breaks down the chemical bonds and releases energy. And it flows into another form, heat, mechanical work, depending on what it needs to do. This one burns and drives an automobile. This one gives you energy that you burn off as heat. Any questions? So chemical is a chemical, and food is considered a chemical. Mechanical energy, this is the energy that is stored by virtue of the motion and position of an object. The spinning flywheel on the rowing machine stores mechanical energy. Mechanical energy is sometimes divided into kinetic energy, energy of motion, and potential energy, energy of position. If I climb up to the high dive, I'm gaining potential energy. I've done no work against the force of energy to climb up. I've done work. When I dive, I'm losing potential energy as I fall, but I am moving faster and faster, gaining kinetic energy. When I splash into the pool, my kinetic energy is transferred to the pool. So climbing up, you're building up potential energy, because the higher you are, gravity's pulling on you. And when you jump, then it turns into the kinetic energy. I remember my kids for school had to bring racetrack and cars, and they would build a track. And then when the car sits at the top of the track, that's your potential energy. When you tap it and it goes down, gravity's pulling it, it's turning into kinetic energy. So potential energy is the energy that's sitting there waiting. It has potential and usually turns into kinetic. Any question? Electrical energy, just like it sounds. Electrical energy is what flows when we plug in an appliance. So that comes from electricity. Cars now are starting to get electrical energy instead of chemical energy. But it develops a usable means of energy transmission resulted from the discovery of relationships between electricity and magnetism. The invention of machines like dynamo for converting mechanical energy into electrical energy, and the motor for converting electrical energy into mechanical energy. So different machines, you plug it in, a drill. Now they have battery, but say you still have to charge it. So you plug it into an electrical outlet. That electricity then is going to be used mechanically when I turn the drill on. And so certain things can go from electrical to mechanical, or you can go from mechanical to electrical. Any questions so far? Radiant or electromagnetic energy. This is energy transmitted by electromagnetic radiation, including radio waves, microwaves, infrared heat radiation, light, X-rays. I don't know if you've noticed certain things like radios, even phones, computers. If you're in the room where the microwave is, sometimes they don't run as well. Now, technology, it's changed a lot more than it used to be, but it would interfere with other waves. And that's one way of seeing that radiation or radio waves. Nearly all energy on Earth originates in one way or another from the sun, and energy is transmitted from the sun to the Earth by electromagnetic radiation. We now have many technologies for manipulating electromagnetic energy. Well, then they repeat the same ones. Any questions on that? So the reason that your food cooks faster in the microwave is radiation waves. An X-ray machine is one way of understanding how dangerous they are, because whatever you're X-raying, they cover everything else up to try and limit the amount of radiation that you're getting. Nuclear energy. Nuclear energy is stored in the bonds between the particles of the atomic nucleus. These bonds are much shorter and tighter than chemical bonds, and the energies associated with them are proportionally greater. The energy that powers the sun is generated from nuclear reactions. Managing nuclear energy on Earth for non-destructive purposes has presented many challenges, but has been successful in some contexts. For instance, the nation of France derives about 75% of its electrical energy from a nuclear plant power. I know my nephew was going to apply for a job, and they had nuclear power, and what they wanted was the person had special gear they had to wear, and then they had like a monitor to check how much they were getting, and then they could only work once every like 4 days. But what they did was they had to go in wherever they had these machines. There was like 10 of them in the surrounding area he would be covering, and he'd go to each one of those and make sure everything was running correctly, because they didn't want to have a disaster. But that's dangerous, and for the amount of money he was making, it was not worth it. But they do have people who put the gear on and have this, but they should pay them more. But they can only do it like once every so many days. And then they'd go to all of those places and make sure they're working properly, because it's a good power source, but it's not safe if it's not checked more often than how often we go down and check our hot water tank. So it has to be checked weekly. Any questions on that? Last one is, I think it's the last one. What's the last one? At least in this section, thermal heat energy. It's an important fact that heat is also a form of energy produced by the disordered motion, kinetic energy, on the parts that make up an object. In the example, the diver above, the ordered one-directional motion of the diver is transferred to motion of the pool water, which soon becomes disorderly. In fact, it becomes heat. So heat and motion, you can even think about just running up a flight of steps, you become warm. That's your heat making energy. Rubbing your hands together. So there's a lot of minor ways of thermal or heat energy. Any questions?
No.
It's usually easy to convert other forms of energy into heat. This was an example they had in the book. Well, they had a different picture, but suppose that the climber is rappelling down a cliff. Her potential energy is converted to heat, kinetic energy. When we talked about that, being up at the top, you have that potential energy. And when you start coming down, it turns to kinetic. But it also causes friction with the rope, and the heat is being released in here. And so then the metal clip, if you're touching it, it's going to be really hot because of that friction. So you're causing friction or heat energy. And you started with potential, which turned into kinetic, and this became hot. Any questions? It's also possible to convert heat into other forms of energy. For instance, in a nuclear power plant, nuclear energy is converted to heat. The heat then boils water to make steam, which turns a turbine or mechanical energy, which in turn drives a dynamo to produce electric energy. So we can, from one form, convert it to many others to get the job we need done. But in contrast to the ease with which we can turn other forms of energy into heat, turning heat back into other forms of energy is subject to strict limits imposed by laws of thermodynamics, which we look at a later section. So going back, there's a lot of places where you can cause problems to the atmosphere and things around it. And so there's certain laws you have to follow. And we talk about that. I think it's in the next section. Our society is a big spender of energy. Do you think it's a problem or an opportunity?
Problem.
Could be. But others may think of it as an opportunity. If you think about money for a second, it is perhaps enjoyable to be a big spender, and it may empower you to do a lot of good, but you had better be sure that you have enough money to do that. Well, the same thing when you're talking about energy. If we're going to use a lot of energy to get a lot of power, are we going to run out? And you can think about that with gas. Gas prices keep going up and down. They say it's because there was a storm somewhere, or there's a lot of different reasons. And so then the prices have to go up because they're saying that they're going to run out of our supply. And so that gives you a lot of power, but you have to be careful because you could run out and then you have no power. Either way, the company has no more supply and think of it as the person not having power also. So we need to be careful of our natural resources. If we're using them for power, we could run out. Any questions on that? There's a lot of different units we're going to be using. The most common is a joule, which is J, capital J. That's from the metric system. And that's pretty much metric system pretty much uses just a joule. But the US uses, I think I have it written somewhere. There's like at least five different ones we'll be looking at. But the table that shows you conversions and some estimates is on page 85. There we go. I thought this was a good example. It lets you understand what a joule is. Your phone charger, I don't know how many people do this, but I know after reading this and we were discussing it at my house, a phone charger plugged in but not charging for 5 seconds is 1 joule. Well, I think that we have at least 5 phone chargers plugged in right now and nobody is home. We just don't unplug it. So then we were talking about ways that we could take care of this. If we didn't want to unplug it, we could hook it to a power surge and then just shut it off before we left. Or we can plug it into one of the outlets that has a light switch. But every 5 seconds, we're using 1 joule. Well, if it's plugged in for the 8 hours I'm gone for the day and I'm not even using it, that's a lot of seconds, which is a lot of joules, which would be wasted because it's not like you're using it. Heat water for a cup of coffee, 10 to the 5th, that would be 5 zeros, 100,000. Food energy in large cookie that you will eat with your cup of coffee, 10 to the 6th. Chemical energy in 1 gallon of gasoline, 10 to the 8th. These numbers are getting large. But some of these we need. The phone charger being left in, we don't. And then if you think of all the other things that you leave plugged in that are not charging at that time, I have a computer charger at home and then I don't have to carry it to school. I have one at school. So there's always one left plugged in that's not charging my computer. And that would probably be a lot more than a phone charger. So these are different things. And if you were asked, let's see, the US electrical energy generated by wind power during 2016. So I would think that would mean a whole year was this value. And all sources the same period. This one. Let's see. Heating water for a couple. Let's look at the phone charger. So I don't know. How many phone chargers do you think that the average household has plugged in?
4 or 5.
Okay. So 4 to 5. We'll round that to 4.5 chargers.
If we have a phone charger that has 2 USB ports on it, do you think that's still 1 joule?
I think so. I think that when it's not being used, it probably still holds the same amount in it. That's a good question. Maybe it would be, I don't think it would be as much as 2 though. But yeah, it might be a little more. I have to do research on that one. Because it would need more power, so it probably draw more. I don't think it would draw 2 though. Let's see, what do we need? If we want to find out how many joules we're using in a day in the United States. What else would we need to know? We know 1 joule, 5 seconds. How many households there are?
What?
If we wanted to know how many joules we're using per day when we are not charging a phone, we said there's around 4.5 chargers per home. We said that 1 joule is 5 seconds. The household, we need to know how many households there are in the US.
The 500 million?
I don't know, there's only 320 million people,
Mm,
but we could Google it. How many? $124 million. Let's see. So I'd say 124 million.
so are we trying to find the amount of joules spent in a day?
Yep. So we have 4.5 chargers per home, 124 million homes. I guess we need to know how long in one day is it left with no phone on it?
Considering people sleep for 8 hours, give or take.
So
Technically in my household, we just never unplug them. We just plug our phones in whenever we need it, but the charger always stays plugged in.
So if we're using it for 8 hours, how can we find out how many hours it's plugged in and not being used in a day?
We multiply the 5 seconds by whatever it is to get an hour.
Okay, yeah, we will need to do that. But if we use it for 8 hours, we don't use it for 24 minus 8.
16.
16 hours, yeah. So it's sitting there for 16 hours using energy. Now we know how many joules in 5 seconds, so we need to get this to seconds. So go ahead, we want to convert this to seconds, because we know it's plugged in one day for 16 hours. And not being used.
11,520 seconds, but it'd be multiplied by 60 and then by 60 again.
Because we know there's 60 minutes in an hour. And I put hour on bottom, so those would cancel. And then we know 1 minute is 60 seconds. And I put minute on bottom, so now I have seconds. To convert to joules, we know that 5 seconds is 1 joule. And I put seconds on the bottom so that it would cancel. Now we could find this value out first. So if we figure this 16 times 60 times 60 divided by 5. Now this was 1 charger.
So we multiply that by 4.5.
And that would tell us, yeah. So if we take that. We know there's 4.5 chargers in 1/2 home. And we know there's 124 million homes in the US. That will tell us how many joules there are in the United States every day.
Six.
Why?
42816 to the 12th power, or times 10 to the 12th power.
1, 5, 2, I didn't calculate it yet.
Ah, you silly goose.
Let's see. Sorry, typed everything right. Yeah. So 6.42816 times 10 to the 12. So 6 times 10 to the 12th. If we look over here, make it a little bigger. Right here. Notice that ours is a 6 times 10 to the 12th. This is 3 times 10 to the 12th. This energy that we use in 1 day could heat a campus for a day. So what we do in 1 day could heat 2 days for a campus. And it's energy that we're not even using. It's just because we left it plugged in. Any questions on that? So even though it doesn't seem like a lot when you think 1 joule for 5 seconds, but when, I mean, I know this is one that a lot of people do. It's just, you don't think about it. Now, notice that if we all keep doing that, we could steam heat a campus for 2 days in what we use in 1 day. Any questions on that?
Could you move over your
Yeah.
paper
Everyone's
slide
going to go home and unplug their phones, right?
equation?
Plug my
Phone
charger.
chargers.
Yeah.
Any questions on that?
Could you scoot your paper over a little bit so I can see that full equation?
Oh, yeah.
Thank you.
Any questions?
No.
Has everyone got it? Now, of course, if you were asked to do this on a test, on a project, your values can be different. They don't have to be exact. And you can just estimate certain values, but if you think you're going to be way off, think about what your estimate would be and then Google it like we did. And I mean, you can even put that in. At first, I thought it would have been 150 million, but it's only 124 million. Then that's fine. Or just put where you got your average from. Make sure you cite that website. On an in-class one, I would give you those values. You should know the population of the US is 300 and some million. 330 is a good estimate, but somewhere in 300 and some million. Yeah. And then 7 billion to 8 billion for the world. So somewhere between the 7 to 8 billion, that is the one that you should know. You are a lot of formula sheets, so you could have that on there. Actually, it is on there if you use the large numbers. Under, I think it's under outlines. Conversions to know. Doesn't, oops, there it goes. There we go. You could print this out and have it out for your test. The approximate value for the US 336 million, approximate population 7.9 billion. But I will take anywhere in the 300 million. And then it's getting, it used to be when I first taught this class 7.2 billion and now it's 7.9. It's growing quickly. But these are values you should be comfortable with. I'm not saying you have to memorize them because you can have a formula sheet. And they are on as you learn. Under outlines. Right there. Any questions on that?
No.
All the processes of industrial society rely on the availability of energy, manufacture, transportation, food systems. So all of these rely on energy. Energy is not substitutable. Economists use the word substitution to say that one good can take place of another. If I don't have an apple, I can eat a banana. If I run out of tea, I can drink coffee or perhaps beer. Margarita would be better. Substitution can take place within energy sectors. A power plant can burn natural gas instead of coal. So we can find different ways of using or different energy for some things, but the laws of thermodynamics tell us there can be no substitution for energy as a whole. So they don't mean that you can't like substitute. It was talking about coal instead of natural gas. That can be a substitution, but there's, well, when we get to this one in the next chapter, it'll be easier to see. But it says you cannot substitute energy as a whole. The majority of our energy, so small. The majority of our energy needs are presently met by burning fossil fuels such as coal and oil. Fossil fuels store the energy of ancient sunlight that fell on Earth millions of years ago. But they are finite resources. Finite resources means that you could run out. There's only so much. It seems likely that we may approach the limits of these resources, especially of easily extracted oil and natural gas within a human time scale, a few generations. Whether or not this is the case, there is no doubt that our present use of fossil fuels is non-renewable. It's a one-way process. It's not making more. So once you use it, it's gone. If you think of a child gets, maybe when they turn 16, a certain amount into an account, and that's what they have. And if they're not working, they're not putting money into it. Once it's gone, it's gone. You can't get it back. And so that's how these work. Fossil fuels are non-renewable, or once they're gone, they're gone. The earth is not making more of them. Drawing power from a AA battery. Once the energy in it is gone, it's gone. You can't recharge it. The burning of fossil fuels also releases carbon dioxide into the atmosphere, and we talked about that yesterday, how much was going into the atmosphere, and we didn't have enough to replace it. This gas remains in the atmosphere for thousands of years, and the amounts that have been released by fossil fuel burning so far are already sufficient to affect the Earth's climate. Scientists believe it's very probable that continued fossil fuel burning will have highly disruptive and negative effects on the climate and the planet's capacity to support life. And so these are just some things to think about. I know that they've passed a lot of laws like to help with the carbon dioxide. If a company, say there's a corner piece of land and there's some trees there, even if they weren't healthy, if they cut it down and put a building and then they put a parking lot, if you're noticing now the parking lots that are going up, there's all kinds of plant and trees in them. Depending on how big the lot is, you have to have so many trees in that area to help sustain and keep the carbon dioxide from building up. So even though you're putting in a parking lot, say there's a parking lot down the street and it had no trees in it. Well, this other company bought it and replaced the parking lot. They had to put trees in because of the new law. And so we're trying to do things like that to keep things better by adding the trees. Well, there's a lot of other laws. I was thinking of them when I read the one, but I forgot what it was. Like the batteries, we used to recycle them. They're saying we don't need to now, but I think that's just because people are lazy and don't want to. But your batteries should be recycled. There should be a spot on campus. Most campuses have like bins and you just throw your batteries in it. Any questions on that?
No.
Close. I don't know why it won't close. Oh no, I hit the wrong button. This one. There we go. I think it's on the next page. Yeah. Here are a lot of the US conventional measurements. The foot pound, which we talked about, BTUs, British thermal units, food calorie, kilowatt hour, and quad. So these are US measurements. They converted them to joules. That way they're easier to compare. Notice a foot pound, 1.4 joules. So 1.5 of them would be leaving your plug in on your phone. But then I like that they give little examples. Work done in moving a distance of a foot against resistance of a pound. But they're kind of notice there are two different things you're comparing. Energy needed to heat a pound of water through 1 degree Fahrenheit. 1 degree Celsius, notice it takes a little more because 1 degree Celsius and 1 degree Fahrenheit are not the same. Last chapter, we had a formula chart. If I probably will give a problem on the test where you're converting the units to make sure you understand the equations, but I will give that chart or the conversions so that you have the equation. Any questions on that?
These charts are also in the ASU Learn stuff.
Yeah, this is in your
Yeah.
book. So this would
Okay.
be page 85 and 86.
Okay.
Yeah, so these are good ones. Whenever you're asked a question on the problems, I guess I will try and remind you to look at the table. That way you know where to go to find certain values. But on a test, these tables I would give you, or I'd give you the conversion. So if I was asking you to change so many foot-pounds to joules, I would either give the table or tell you 1 foot-pound is 1.4 joules.
Okay.
Any questions? Okay, so tomorrow we'll do, not tomorrow, tomorrow's Thursday. Friday we'll do some problems in this section, and maybe hopefully finish 2.3 on Friday.